Hello. Yeah, interesting, huh? What's interesting? What is it so interesting? Hmm. Well, today is gonna be about a bunch of, yes, research and science and stuff like that. So let me just move some things around. Hey, look, it's a me. I am here. Here I am. Here you are too. Hello, hello. Yeah, so as I said to you, yes, today we have research things. What kind of research maybe you're thinking? Well, we're gonna talk about a few very interesting science things. I decided to be a little bit of a different one. I don't like this song. This song, let me change it. This is better. We have sci-fi music. We have science music. Science music. Let's go. Because we're a bunch of nerds. So I decided to talk about a bunch of again science facts that I thought that they're gonna be a little bit interesting for everyone here. And while the research, is not very thorough, and I didn't do exactly a lot of wow. Don't think about stuff that are way over above, like these are just going to be just like base uh, facts that you can find everywhere and anywhere. But I thought, why not try to get a little bit more deep? While I do like to play games a lot and dating simulators and stuff, I think we should dive more into like nerd stuff too. So it's a good thing to, share opinions and things. I can read you guys, and then you can tell me what your opinion is about this certain thing. Okay, so let's get into it, shall we? The first subject I'm going to talk about today, it is maybe something that you've heard before, and that is the string theory. String theory. No problem. You can think that I'm a podcast about science stuff. So, and yes, thank you. But and have fun with D&D. But yes, so as I said, the first thing we are going to talk about in today's stream is the string theory. So, in physics, the string theory is a theoretical framework in which the point-like particles of particle physics are replaced by one-dimensional objects called strings. String theory describes how these strings propagate through space and interact with each other. On distant scales, larger than the string scale, a string acts like a particle, with its mass, charge, and other properties determined by the vibrational state of the string. In string theory, one of the many vibrational states of the string corresponds to the gravitation, a quantum mechanical particle that carries the gravitational force. Thus, string theory is a theory of quantum gravity. The string theory was first studied in the late 1960s as a theory of the strong nuclear force. Before being abandoned in favor of quantum chromodynamics, subsequently it was realized that the very properties that made string theory unsuitable as a theory of nuclear physics made it a promising candidate for a quantum theory of gravity. The earliest versions of string theory, bosonic string theory, incorporated only the class of particles known as bosons. Don't think about bad stuff. It later developed into superstring theory, which posits a connection called supersymmetry between bosons and the class of particles called fermions. 5 consistent versions of superstring theory were developed before it was conjured in the mid-1990s. That they were all different limiting cases of a single theory in 11 dimensions, known as the M theory. In late 1997, theorists discovered an important relationship called the anti-de Sitter conformal field theory correspondence, ADS-CFT correspondence, which relates string theory to another type of physical theory called a quantum field theory. Yes, the bosons. Okay. Now, let's have a little bit of an overview. Maybe you guys are thinking, like, who was the first person who actually did any kind of put any kind of thought into this? Well, in the 20th century, 2 theoretical frameworks emerged for formulating the laws of physics. The first is Albert Einstein's general theory of relativity, a theory that explains the force of gravity and the structure of space-time at a macro level. The other is quantum mechanics, a completely different formulation, which uses known probability principles to describe physical phenomena at a micro level. By the late 1970s, these 2 frameworks had proven to be sufficient to explain most of the observed features of the universe, from elementary particles to atoms, to the evolution of stars and the universe as a whole. The starting point for string theory is the idea that the point-like particles of particle physics can also be modeled as one-dimensional objects called strings. String theory describes how strings propagate through space and interact with each other. In a given version of string theory, there is only one kind of string, which may look like a small loop or segment of ordinary string, and it can vibrate in different ways. On distant scales, larger than the string scale, a string will look just like an ordinary particle consistent with non-string models of elementary particles, with its mass, charge, and other properties, determined by the vibrational state of the spring. String theory's application as a form of quantum gravity proposes a vibrational state responsible for the gravitation, a yet unproven quantum particle that is theorized to carry gravitational force. Yes. Now, let's talk about extra dimensions. In everyday life, there are 3 familiar dimensions, 3D, of space: height, width, and length. Einstein's general theory of relativity treats time as a dimension on par with the 3 spatial dimensions. In general relativity, Space and time are not modeled as separate entities, but are instead unified to a four-dimensional, 4D, spacetime. In this framework, the phenomenon of gravity is viewed as a consequence of the geometry of spacetime. String theories require extra dimensions of spacetime for their mathematical consistency. In bosonic string theory, spacetime is 26-dimensional, while in superstring theory it is 10-dimensional, and in M theory it is 11-dimensional. In order to describe the real physical phenomena using string theory, one must therefore imagine scenarios in which these extra dimensions would not be observed in experiments. But yeah, what do you guys think about this, huh? Did you think I was only thirsty? No, I can talk about science. Insert GIF with with Jesse from Yes, science. Smart and dangerous. Not really. But yes. At the end of it all, I wanted to choose to talk about the string theory because for me it's very interesting how basically we can just live in this like small part of a dimension, because that's basically what it is. We're not just thank you. We're not just little particles in the universe, but also we're just little particles in the dimension, which is very interesting to think about it this way. While Einstein had his things and stuff of saying, we need to also realize that a long time things can change. Okay. Do you guys have any thoughts, opinions regarding the string theory? Do you also have things that you would like to talk about? Like, do you have also like your opinions and your elements that you've been finding? I guess it's safe to say we can move to the next subject. And the next subject is the simulation hypothesis. You know that you always have to say things like, "Oh, we live in a simulation. What in the Matrix is happening with my life?" Well, yeah. Then let's not forget, we're not the only ones who believe this. Those are goodies. Yeah. I mean, everyone has the idea that they live in a simulation, right? Like, no, we live in a simulation. The chicken tastes like chicken, yeah. But let's get real now. The simulation hypothesis proposes that what one experiences as the real world is actually a simulated reality, such as a computer simulation in which humans are constructs. There had been much debate over this topic in the philosophical discourse and regarding practical applications in computing. This assumes that consciousness is not uniquely tied to biological brains, but can arise from any system that implements the right computation structures and processes. Have you ever seen your neighbor bringing in groceries? No, Jay, you thought you did. Let's think. Let's see about the origins of this simulation hypothesis. Human history is full of thinkers. Oh, it is. Who observe the difference between how things seem and how they might actually be. How Alpha said, have you ever seen your neighbor bring in groceries? With dreams, illusions, and hallucinations, providing poetic and philosophical metaphors. For example, the butterfly dream of Zuganzi from ancient China, or the Indian philosophy of Maya, or in ancient Greek philosophy, where Anazarchus and Monimus linked existing things to as Gnosticism's was the belief that reality, as we experience it, is the creation of a lesser, possibly malevolent deity from which humanity should seek to escape. Oh no. Are we back? Oh my god. Are we back? I just realized I got disconnected. Oh no. Oh yeah, we are back. Okay, good. We're back. Sorry, I don't know what happened. Jesus. That was weird. Oh well. Anyway, I'm gonna go back. So, I'm gonna go back to the last thing you guys heard. So, a common theme in the spiritual philosophy of the religious movements collectively referred to by scholars as Gnosticism was the belief that reality was the experience it is the creation of a lesser, possibly malevolent deity from which humanity should seek to escape. You know how we always say that there's a lot of people being like, oh, I am not, what do you call it? I am not led by anything in the world. I am my own God. I am my own master. That's not really the case. Some people think that everything you do, it's meant to happen, or you've been led to that point in your life, or you've been led to that point to make that specific choice in your life, which might be possible. You don't know. It's a theory. Anyway. In the Western philosophical tradition, Plato's allegory of the cave analogized human beings to chained prisoners unable to see reality. René Descartes' evil demon philosophically formed these epistic doubts, to be followed by a large literature with subsequent variations like Brain in a Vat. In 1969, nice, Konrad Zuse published his book Calculating Space on Automata Theory, in which he proposed the idea that the universe was fundamentally computational, a concept which became known as digital physics. Later, roboticist Hans Moravec explored related themes through the lens of artificial intelligence, discussing concepts like mind uploading and speculating that our current reality might itself be a computer simulation created by future intelligences. Which that this last one is actually very, very known if you think about it. Because, yep, I've seen it. I've seen it happening before. Anyway, so what is the argument of this? It is possible to simulate consciousness, and advanced civilizations run many such simulations. The number of simulated realities will vastly outnumber the single base reality. Um, the origin. The concept stems from historical thought experiments regarding the nature of reality, such as Plato's allegory of the cave and Rene Descartes' evil demon. Scientific perspective, we can say that some proponents like Rizwan Verk argue that the development of virtual reality in video games mirrors the progression towards potentially simulating entire universes. But as in anything, we also have criticism. And these might be first the physical limitations. Recent studies suggest that simulating even small amounts of quantum materials requires impossible amounts of energy and memory, making the simulation of the entire universe unlikely. So, basically, but that would require a lot of energy and memory. So, in order for the aliens to play Sims with us, that will require a bunch. We also have unfeasibility. Critics argued the hypothesis is more of a philosophical or religious belief than a scientific theory, as it cannot be proven or disproven. As anything, it has its ups and downs, its pros and cons. And it's funny enough that you said that Sims, that the aliens are playing Sims, but we also have the pure Sims versus biosims. The theory suggests beings could either be purely algorithmic or biological entities, biosims, whose brains are connected to a simulation. So, at the end of it all, the hypothesis has become a major topic of debate, with viewpoints ranging from viewing it as a plausible future of humanity to considering it a modern myth. So, we don't know. Do we live in a simulation? Maybe. Maybe not. Right? And the third subject of today, it was between two things, but I chose the one that maybe will be more interesting to follow. And that is the dark matter. Don't we love the dark matter? Yes, we do. So, in astronomy and cosmology, dark matter is an invisible and hypothetical form of matter that does not interact with light or other electromagnetic radiation. Dark matter is implied by gravitational effects that cannot be explained by general relativity unless more matter is present than can be observed. Such effects occur in the context of formation and evolution of galaxies. Gravitational lensing, the observable universe's current structure, mass position in galactic collisions, the motion of galaxies within galaxy clusters, and cosmic microwave background anisotrophies. Yes. So, dark matter is thought to serve as gravitational scaffolding for cosmic structures. After the Big Bang, dark matter clumped into blobs along narrow filaments with superclusters of galaxies forming a cosmic web at scales on which entire galaxies appear like tiny particles. So, our galaxy is just a little speck of dust in the all big. Dark matter is not known to interact with ordinary biomagnetic matter and radiation, except through gravity, making it difficult to detect in the laboratory. The most prevalent explanation is that dark matter is some as yet undiscovered subatomic particles, such as either weakly interacting massive particles, also known as WIMPs. Yes, WIMPs. Or axions. The other main possibility is that dark matter is composed of primordial black holes, which that's interesting. Okay, let's see a little bit of history about this. The hypothesis of dark matter has an elaborate history. Lord Kelvin, very known, discussed the potential number of stars around the Sun in the appendices of a book based on a series of lectures given in 1884 in Baltimore. He inferred their density using the observed velocity dispersion of the stars near the Sun, assuming that the Sun was 20 to 100 million years old. He posed what would happen if there were 1,000 million stars within 1 kiloparsec of the Sun, at which distance their parallax would be 1 milliarcsecond. So Kelvin concluded many of our supposed 1,000 billion stars, perhaps the great majority of them, may be dark bodies. This went dark all of a sudden. No pun intended. The second to suggest the existence of dark matter using stellar velocities was Dutch astronomer Jacobus Kapteyn in 1922. A publication from 1930 by Swedish astronomer Knut Landmark points to him being the first to hypothesize that the universe must contain much more mass than can be observed. Dutch radio astronomy pioneer Jan Oort also hypothesized the existence of dark matter in 1932. Oort was studying stellar motions in the galactic neighborhood and found the mass in the galactic plane must be greater than what was observed. But this measurement was later determined to be incorrect. The hypothesis of dark matter largely took root in the 1970s. Several different observations were synthesized to argue that galaxies should be surrounded by halos of unseen matter. In 2 papers that appeared in 1974, this conclusion was drawn in tandem by independent groups. In Princeton, New Jersey, by Jeremiah Ostreicher, Jim Peebles, and Amos Yahiel, and in Tartu, Estonia, by Jan Enastio, Ensar, and Ans Kasik. At the same time, radio astronomers were making use of new radio telescopes to map the 21-centimeter line of atomic hydrogen in nearby galaxies. The radial distribution of interstellar atomic hydrogen often extends to much greater galactic distances that can be observed as collective starlight, expanding the sample distances for rotation curves, and thus of the total mass distribution, to a new dynamical regime. Early mapping of the Andromeda galaxy with the 300-foot or 91 meters telescope at the Green Bank, and the 250-foot or 76 meters dish at Yodel Bank already showed the atomic hydrogen rotation curve did not trace the decline expected from Keplerian orbits. A stream of observations in the 1980 to 1990s supported the presence of dark matter. Persic, Salucci, and Stell in 1996 is notable for the investigation of 967 spirals. The existence of dark matter also included that gravitational lensing of background objects by galaxy clusters. The temperature distribution of hot gas in galaxies and clusters, and the pattern of anisotropies in the cosmic microwave background. The prevailing view among cosmologists remains that dark matter is composed primarily of some type of not yet characterized subatomic particle. While this remains the majority opinion, the lack of particle detection has led to a divergence in consensus, with microscopic candidates such as primordial black holes seeing renewed interest following observations by LIGO and JUST. The research for such particles, by a variety of means, is one of the major efforts in particle physics. So, what do we know? We know that the composition is this one. Dark matter constitutes about 85% of the total mass in the universe, whereas ordinary matter, stars, planets, gas, makes up less than 5%, which is crazy. So, dark matter is everywhere. Anyway, first discovery is, we'll say that the term was coined in 1933 by Fritz Zwick to explain the rapid motion of galaxies within the Coma cluster, which suggested hidden mass. Hence why it's called dark matter. Function, it can act as an invisible glue or scaffolding, forming a cosmic web that structures the universe. Basically, the dark matter is at the base of everything. For the dark matter, the things that we know in the universe wouldn't be held together as they are. The detection of it, while its nature is unknown, scientists detect it through gravitational lensing and its influence on the rotation speeds of galaxies. But also hit with something else that's interesting, which are called the dark galaxies. Some galaxies, such as CDG2, are composed almost entirely of dark matter, with very few stars. See, this is what they call dark galaxies. It's just, you're dark, man. Somebody close it, somebody turn off the lights. But yeah. So isn't this interesting? It is. What do you guys think? Did you ever wondered what is the dark matter and why are so many people in sci-fi movies talking about it and why is this so important? Well, here are your answers. Do with them as you please. Yeah, don't shoot the messenger. I'm just here to talk about it. Want to hear more about the dark matter, or you want me guys to jump to a different subject? I can do both. Whatever you want. It is very fun. It is. Like, let's talk more about it. So, how do we know it's there? Astronomers noticed things that couldn't be explained by visible matter alone. Galaxies rotate too fast. The other stars should fly off if only visible mass were holding them in. Galaxy clusters stay bound together more strongly than expected. Light bends, gravitational lensing, around massive regions where not enough visible matter exists. Like the moon, for example. The structure of the universe, how galaxies formed and clumper, matches models that include a lot of unseen mass. So that's how we know there. As I said earlier, if it wasn't for the dark matter, yes, it wouldn't be gravity. So but you guys wondered what would happen if dark matter didn't exist? Well, if dark matter didn't exist, the universe would look very different and probably much simpler, emptier, and less structured. So, galaxies might never have formed, or would be tiny and rare. Dark matter acts like an invisible gravitational scaffold that helped pull ordinary matter together after the early universe cooled. Without it, gas would have spread out more evenly. Gravity from normal matter alone would be too weak to form large galaxies quickly, and many galaxies, like the Milky Way that we're in, might never have formed at all, or would be much smaller and looser. The universe could be mostly scattered stars and small clumps rather than vast spiral and elliptical galaxies. Or existing galaxies wouldn't hold together well. Right now, galaxies spin so fast that visible matter alone isn't enough to keep them bound. Without dark matter, other stars would drift away into space, galaxies would slowly unravel, large systems like the Andromeda galaxy might not stay stable for billions of years. Galaxies would be more fragile and short lived. Another thing, the cosmic web wouldn't exist. Today, matter in the universe forms a huge cosmic web, filaments of galaxies separated by enormous voids. Dark matter helped shape this structure early on. Without it, matter would be distributed much more smoothly, fewer clusters and superclusters, and a more uniform, less dramatic universe. You know how you're looking at like things on the internet, like when there's those, even on TikTok, you see those beautiful like shots from the universe. Yes, those very amazing and gorgeous things that you see, they wouldn't exist if it wasn't for the dark matter. They wouldn't be able to hold together. Another thing, star formation would be slower and less efficient. Dark matter's gravity helps gather gas clouds that collapse into stars. Without this, star formation would take longer, fewer stars overall, and possibly fewer heavy elements like carbon, oxygen, or iron, which form inside stars. That means fewer planets, and maybe even fewer chances for life. So, without dark matter, the universe would likely be less structured, less dense in galaxies, slower to form stars, and possibly less capable of supporting complex life. So without dark matter, would be no life. Or not the life we know right now. So everyone thank dark matter. Everyone say thank you, dark matter. Thank you. Thank you for keeping us alive and for not letting things happen and for making things happen, even better said. Okay. I think we talked about dark matter enough. What do you guys say we move to the next subject? Oh my god! That's actually true! Dark matter shortened would be DM. So see that everything makes sense now. Even D&D knows. D&D started it. Okay. Well, I think it's time for us to move to the next subject, which is the Fermi paradox. One of the biggest unanswered questions in science. If the universe is so huge and old, where's everybody? It's named after physicist Enrico Fermi, who famously asked this question during a casual lunch conversation in 1950. Because that's what you do at the lunch in 1950. If the universe is so huge, where is everybody? Yeah, where the fuck is everybody, mate? Anyway, why the paradox exists? Well, the universe seems incredibly suitable for life, right? There are hundreds of billions of galaxies that we just talked about because of the dark matter is holding them, each with billions of stars. Many stars have planets. Some planets should be Earth-like. Or are Earth-like, right? The universe is 13.8 billion years old. Plenty of time for intelligent civilizations to arise and spread, right? Right. In our Milky Way, there are billions of potentially habitable planets. So statistically, intelligent life should be common. Yet we see no confirmed signs. No signals, no probes, no visitors. That mismatch between expectation and observation is the paradox. So, what the fuck? Major explanation scientists consider might be that there's no agreed answer. But here are the leading ideas. Intelligent life is extremely rare. I mean, look at humans. They're not the best peas in the pod, but they may do. intelligent life is extremely rare, okay? So maybe simple life is common, but advanced civilizations almost never evolve. And the possible reasons are life rarely starts, complex cells are rare, and intelligence is an evolutionary fluke, which humans somehow got it. Ew. Anyway, another one would be civilizations destroy themselves, as the humans are doing right now. Advanced societies might not last long. The possible causes would be a nuclear war, which I'm seeing it coming, climate collapse, which I'm seeing it coming, artificial intelligence risks, which I'm seeing it coming, and resource depletion, which I'm seeing it coming. If most civilizations go extinct quickly, the galaxy stays quiet. It's not like the galaxy is gonna the galactic news. Another civilization died. We're sorry to inform you. But yeah. The third one might be that they exist, but we can't just detect them. Maybe they're out there, but signals are too weak or short lived. They use communication methods we don't understand, which that's very possible. They deliberately stay silent because they're like that kind of people that are like, why should I care? I give a shit about my neighbor. They don't give a shit about me. They're too far away for contact. Which that's less possible, but anyway. So search efforts like CETI Institute are trying to detect possible signals. As we know, NASA has been trying for many a years to do so. Anyway, another one would be that we're early. Humanity may be among the first intelligent civilization to appear in our region of the universe. The galactic party, quote unquote, might just be getting started. So maybe we're first. But that's just like a thing, it was like a little bit of a narcissistic point of view. Oh, look at us, we're so intelligent. Oh my god. Or the last one might be the zoo hypothesis. Advanced civilizations know about us but avoid interference, like humans observing animals in the wildlife reserves. Which is also possible. At the end of it all, who would want to talk with us, right? Right. So, why the paradox matters? It forces us to think about how common life really is. The long-term survival of civilizations and humanity's future in the cosmos. And possibly the most unsettling idea, why be alone, or nearly alone, in the observance of the universe. So, yeah. Have you ever thought about this? But as many of things are, to explain different things, we also have a theory. Because you know how people are, they just love to make theories. So the most common theory about this and why are we not finding anyone else would be the Great Filter theory. And the Great Filter theory is proposed. Okay. Bye-bye. Well, good luck to work. Okay, so the Great Filter theory is a proposed answer to the Fermi paradox. It suggests that something prevents most life from becoming advanced, spacefaring civilizations. And the idea was developed by economist Robin Hanson. Anyway, the core idea. Imagine the path from dead matter to intelligent interstellar civilization as a long chain of difficult steps. The Great Filter is one or more of those steps that is extremely unlikely to pass. That's why we don't see the universe full of advanced aliens. Almost no one makes it all the way through. So, where could the filter be? There are two big possibilities, and each has very different implications for humanity. So, the first one would be that the Great Filter is behind us, which are the good news. Something in the past is incredibly rare, and Earth already passed it. Possible rare steps. Life starting at all, after the Big Bang and everything. Complex cells evolving. Yeah. Multicellular organisms forming. Intelligence evolving. Technological civilization emerging. If this is true, then intelligent life is extremely rare, even as a huge galaxy like the Milky Way. That would mean humanity is special, which, yeah, again, that's a bit narcissistic, but oh well, we're humans. The universe is quiet because almost no one ever reaches our level. Get on my level. Kind of situation. Okay. But we also have the bad news. The Great Filter is ahead of us. Advanced civilizations may commonly arise, but they don't survive long. Possible future filters: self-destruction, war, or environmental collapse, which is very possible, especially what's happening right now in the fucking world. But oh well. Uncontrolled artificial intelligence, which is another one that's very possible. We also have the resource exhaustion, which is very possible. Technological disaster, which is also possible. Or unknown cosmic threats. Yay. If this is true, then most civilizations reach our stage and then die out before spreading through space. So the silence of the universe becomes a warning. And something deadly may lie in humanity's future. Ha ha ha. Be afraid. So, why discovering alien life will matter so much? Are you wondering? This is the most dramatic implication, okay? If we found simple life elsewhere, for example, microbes on another planet, that would suggest early steps are easy, which means the Great Filter is probably still ahead of us. That's why some scientists say discovering alien bacteria could actually be bad news for humanity's long-term survival. Good thing we found them in the ocean a while ago. Does anyone remember that? Shut up! Shut up, Jay! Anyway, why the idea is so powerful, okay? The Great Filter reframes the cosmic mystery into survival question. Is humanity incredibly lucky or living on borrowed time? We don't know yet, and that uncertainty is what makes the idea both fascinating and unsettling. So, fun times! Science. Yeah, but really now, Jay, who gives a shit about Mars? Don't know. It is theorized that people have been on Mars, you know? So that might be actually bacteria from some people that were there before. We don't know. It is insane. At the end of it all, I mean, if you're thinking about it, there's been a bunch of those kind of things that um, they literally discovered, like in other. Uh, they discover other universes and they discover planets. Yeah, yeah, yeah. They discover planets that are basically like almost as inhabitable as Earth. So that's also a possibility of like, wait, we might still not be lonely in the universe, you know? You don't know. We don't know. I don't know. You don't know. Nobody knows. They're just theories. Let's hope it's not a bad thing though. Yeah, me too. We too. Me too. We too. We too. We too. Me too. You too. Me too. I am. I mean, there may be so many theories about what's under there too, you know? What might be under the ice of Jupiter's moon Europa? What might it be? Ooh, actually. Yeah, just a ghost leviathan. Nothing too big. Anyway, hey, let's see theories. Actually, I look it up, like theories about like what's under. Let's see what are some theories about like what's under the ice of Jupiter's moon? Because now I'm actually curious. What are some theories that people think about? Let's see. Okay, so scientists think a lot could be hiding under the ice of Europa, one of the most intriguing moons of Jupiter. So let's see what those are. A global liquid ocean. The strongest evidence suggests Europa has a huge saltwater ocean beneath its icy crust. The ice shell may be about 10 to 30 kilometers thick, but estimates vary. Below that could be an ocean of like 60 to 150 kilometers deep, deeper than all of Earth's oceans combined. Measurements of Europa's magnetic field and surface cracking patterns strongly support this idea. This ocean exists because gravitational tugging from Jupiter flexes the moon, generating internal heat that keeps water liquid. Interesting. A liquid ocean. An actual ocean. Imagine. An ocean. Huh. Okay. Let's see what other things. Hydrothermal vents on the seafloor. If Europa has a rocky seafloor, which is very likely, scientists think it may have hydrothermal vents, similar to those on Earth's deep ocean floor. These vents could release heat and minerals, create chemical energy, support ecosystems even without sunlight. On Earth, entire communities of life thrive around such vents. Hmm, you know what that means? Aquatic life can be possible if that's the case. Which leads us to the next one, possible extraterrestrial life. This is the big one. Europa might have the three key ingredients for life: liquid water, chemical nutrients, and energy sources. That makes it one of the best places in the solar system to search for life beyond Earth. Scientists imagine possibilities like microbial life in the ocean, ecosystems near seafloor vents, and maybe even more complex organisms. Pure speculations, but not impossible. So, Jay, you might be right with that or Ghost Leviathan. Anyway, the ice shell itself may not be solid all the way through. There could be subsurface lakes trapped in the ice, warm rising plumps of water, and cracks where ocean water pushes upward, possibly erupting into space. Some observations hint that Europa may even spray water plumes into space, which spacecraft could sample. That would be so cool! The spacecraft NASA is sending the Europa Clipper mission to study the moon in detail, measuring ice thickness, mapping chemistry, and searching for signs of habitability. Future missions may eventually drill through the ice or send a robotic submarine into the ocean. Hmm. Oh my god, now I'm excited. Now I'm excited. This would be the least likely, if you ask me, because if you would ask me 10 years ago, I wouldn't even think of the idea that we would find life on Jupiter or on one of Jupiter's moons, which is even more extraordinary to think that you can find life on a moon. We don't even know if our moon has life, let alone other people, other planets' moons. Not fair. Now I'm jealous. Why can't we be as cool as Jupiter, huh? Yeah, we do, but as I said, why can't our moon be as cool as Jupiter's? Why does Jupiter have to have the more badass moon? Why is our moon so boring? Oh well, I guess that's that. Oh, let's move to the last subject of today's stream. Ugh, and not my neck cracking like a motherfucker. No, it's quantum entanglement. Yay. So, quantum entanglement is a phenomenon in quantum physics where two or more particles become linked so strongly that their properties stay connected, no matter how far apart they are. This actually goes good with the fact that this month is February and we had Valentine's Day. So think about it like that. If you measure one particle, you instantly know something about the other, even if they're separated by huge distances. So take into account long distancers in relationships. Okay, so we have the simple idea first. Imagine two coins that are somehow entangled. You send one to Earth and one to Mars. You flip yours and see heads. Instantly, before any signal could travel, the other coin must be tails. Real entanglement is more complex than coins, but the key idea is their states are not independent. They share one combined quantum state. It's funny how we just got from planets in the universe to quantum entanglement, but oh well. Why it shocked the scientists. When this idea emerged, it seemed impossible. Albert Einstein disliked it and called it spooky action at a distance, which I think that's amazing to call. So he and collaborators proposed a challenge, the EPR paradox, arguing quantum theory must be incomplete. But experiments later showed the weirdness is real. Physicist John Bell developed mathematical tests proving that entanglement predictions differ from classical physics, and experiments confirmed quantum theory. Even Niels Bohr, Einstein's longtime rival in debates, argued this strange connection is simply how nature works. I mean, of course he wanted to be against Einstein, but oh well. So, does this allow faster than light communication? No. Even though the correlation appears instant, you cannot control the outcome of the measurement. So you can send messages this way. Relativity stays safe. No usable faster than light signaling. Take into account. It's also been tested many a times. Modern experiments repeatedly confirm entanglement under strict conditions, even over large distances. Researchers at places like CERN and other labs have verified it with extreme precision. Work demonstrating entanglement's reality and applications earned a Nobel Prize for scientists including Anton Zeilinger. But why it matters? Entanglement isn't just weird. It's useful. Quantum computing, powerful new computation methods, quantum cryptography, ultra-secure communication, quantum teleportation, information transfer, moving quantum states between locations. It's a core building block of future quantum technology. So, what's the big philosophical punch? Entanglement shows that reality at the smallest scales is deeply interconnected, in ways that don't match everyday intuition about space and separation. Particles don't always have independent identities. Sometimes they're part of a single shared system. So, let's talk more about the quantum teleportation. Because if you ask me, that's the most interesting part of it. So the quantum teleportation is a real scientific process where the quantum state of a particle is transferred from one location to another without physically moving the particle itself. It doesn't transport matter like in sci-fi. It transfers information about the particle's exact quantum condition. So the basic idea is that imagine you want to create a particle in a distant lab exactly as it is now. Same spin, polarization, and everything. So the quantum teleportation does this by entangling two particles, one near you and one far away, measuring your original particle together with your local entanglement particle, sending the measurement results by normal communication, like radio or fiber. The distant particle is then adjusted to become an exact replica of the original. But it's important that the original quantum state is destroyed when measured, and the distant particle becomes the new version. So nothing is duplicated. The state is transferred. So, why is entanglement essential? Teleportation works because entangled particles share a single linked quantum system. This connection allows the distant particle to receive the state, but only after classical information arrives. And that's why no faster than light teleportation and no instant messaging. quantum information transfer with perfect fidelity. And it has actually been done. Quantum teleportation has been demonstrated many a times in labs. Major experiments include teleporting photons across kilometers of optical fiber, teleporting quantum states between satellites and ground stations, and transferring states between atoms and separate traps. Pioneering work was done by physicist Anton Zeilinger, whose research helped prove teleportation works and led to a Nobel Prize. As I said before, the first experimental demonstration was proposed and developed by research including Charles H. Bennett. So, why it matters? Quantum teleportation is crucial for future technologies. We have quantum internet, ultra-secure communication networks that cannot be hacked without detection, quantum computing, linking distant quantum processors into powerful distributed systems, long-distance quantum communication, extending secure signals across continents and eventually space. Companies and labs, including IBM, are actively researching these systems. So, what is it not? Quantum teleportation does not move physical objects or humans, scan and rebuild matter, work instantly across space, or function without destroying the original state. Sorry, sci-fi fans. Teleporting a human would require measuring and transmitting an impossible amount of quantum information, and current physics doesn't allow copying unknown quantum states perfectly anyway. So, sorry, no teleportation yet for you. So what's the deep meaning of this? The quantum teleportation shows that information, not matter, may be the most fundamental transferable thing in physics. It reveals how reality is the smallest scale, is governed by relationships and correlations, not just physical objects. Now, still, I am at my heart a sci-fi fan. So, is it or is it not human teleportation be at least theoretically possible? Hmm. Well, short answer, maybe, in principle. But almost certainly never in practice. And even in principle comes with huge philosophical and physical problems. And here's why. What teleporting a human would actually require? To teleport a person the way sci-fi shows, like in Star Trek, physics would be needing to measure the exact quantum state of every particle in your body, transmit that information somewhere else, and then reconstruct an identical arrangement of particles there. A human body contains roughly 10 at the power of 28 atoms, which each with complex quantum properties. That's an unimaginable huge amount of information. And unfortunately, we do not have this yet. So, the biggest physics barriers would be the no cloning theorem. Quantum physics says you cannot perfectly copy an unknown quantum state. So, teleportation cannot make a duplicate. The only way allowed by current physics would be the original must be destroyed during measurement. That means teleportation would be more like scan, destroy, rebuild elsewhere, which raises serious identity questions. It would be like basically you would be reborn. And it's a high possibility that you're gonna lose your memory. So, another one would be that you can't measure everything perfectly. To rebuild someone exactly, you'd need position and momentum of every particle, quantum states of molecules, neural structure and activity, possibly even quantum brain states, if relevant to consciousness. But measuring at that precision would itself disrupt the system. You'd effectively dismantle the person while scanning them, which that would get messy and concerning. Anyway, another one would be information storage and transmission limits. The data required could be far beyond any conceivable storage system, any realistic communication bandwidth, any practical transmission time. Even sending the information at light speed might take extremely long depending on compression limits. Another thing would be that energy and engineering scale. Resembling a human would require precise control over atomic assembly, massive energy manipulation, and perfect error correction. Even a single misplaced molecule could be a catastrophic biologically. Like, again, you would not be you. You'd be basically like you were reborn. And even worse, if any errors appear, you might not get there good. So the philosophical problem, the hardest one, I mean, suppose teleportation works perfectly, okay? Is the person who appears at the destination you? Or just a perfect copy that thinks is you? Your original body is gone, so continuity of consciousness might be broken. Science cannot currently answer whether identity survives this process. So this is known as the teletransportation identity problem in philosophy of mind. So, is it theoretically possible? Depends on what you mean. Transferring full philosophical formation of a human, not forbidden by known physical laws in a purely abstract sense, and reconstructing a functional copy elsewhere may be conceivable in extreme future physics, but again, it requires destroying the original, requires impossible scale, measurement, and control, may not preserve personal identity, and is far beyond any foreseeable technology. Most physicists consider practical human teleportation effectively impossible. But what is realistically possible? Things already demonstrated or plausible would be quantum teleportation of particles in small systems, ultra-detailed biological scanning, and molecular or tissue reconstruction. But it's very far in the future. But full human disassembly and reassembly with perfectly fidelity is many orders of magnitude harder. So the bottom line is human teleportation is not ruled out by pure imagination, not achievable with known technology, probably impractical even for extremely advanced civilizations, and philosophically unsettling even if possible. You might arrive somewhere else. But whether you arrived is the real question. So yeah, sorry. Not teleportation yet, even though that would be so cool. It will also not be very good. Because if teleportation it would be possible, let's be honest. We already know that people are in a very big of sedentaristic lifestyle right now because of many things that can move them from one place to another. So, yeah, I don't think teleportation would be a good actually thing for human health. if you think about it like that. But oh well. But yeah, thing is, that was the last subject of today. We'll see more. Maybe I'll talk more. I'll make like the next episode of Talk Nerdy to Me tomorrow. Or maybe I'll do it next time. Like not next time, like next week, sorry. Either way, I had fun. And I hope you did too. I hope you found my little subjects interesting. But yeah, we'll see what happens tomorrow. Maybe I'll make another episode of this, or maybe I will play a game. Who knows? We'll see. Either way, as I said, hope you have fun. I surely did. But yeah. Bye bye.